In this module, we shall learn about various sampling distributions, namely T, F and chi-square distribution. We have already learned the methods of deriving a sample distribution and the properties of the sampling distribution of mean. The proposition of the sample from a normal distribution and the central limit theorem in conjunction with the properties of the sampling distribution of mean was applied to determine the probability of the mean to lie in a particular specified range. Hence, making use of the properties of sampling distribution of mean and other such properties like the proposition regarding the case of normal distribution and the central limit theorem, we calculate the probabilities of sample statistic to lie in particular specified interval. When we take all the random samples x1, x2, xn from a normally distributed population and calculate the mean statistic of this population using the random sample and form a sampling distribution of mean, the sampling distribution of the mean will also have a normal distribution centered at the population mean. Going another step, if the sample size is sufficiently large, then using the central limit theorem, the sample distribution of mean statistic is also normally distributed at the population mean irrespective of population distribution. The above two results are quite useful. In both the cases, we use the Z tables where the x prime statistic has been normalized and Z is equal to x prime minus mu upon sigma. We can calculate the probabilities of finding the x prime values with a particular specified range. For example, time taken to travel by a ball through the tube variable is normally distributed. Random variable with mu is equal to 1.5 minutes and sigma is equal to 0.35 minutes. A sample of 5 balls is taken and the time taken by them is measured. Then it is specified to us that the total time taken TO ranges 6 to 8 minutes and it has been asked as what is the probability that the total time lies between this range. From the first proposition, we know that the total time TO is also normally distributed when mean n mu and the variance n sigma square. Using these results, we get TO mean equal to 7.5 and TO standard deviation equal to 0.783. So, calculation of probability that C6 is less than TO is less than 8 reduces to calculating 6 minus 7.5 upon 0.783 less than Z less than 8 minus 7.5 upon 0.783 and using the Z table areas behind the Z curve to determine the above values. Similarly, the probability that the sample average time x prime, which is also a normally distributed random variable by the first proposition, is at most 2 minutes, requires mu is equal to 1.5 and sigma is equal to 0.35 upon under root 5, which is equal to 0.1565. Again, the calculation of probability that x prime less than 2 is equivalent to calculating the probability that Z is less than 2 minus 1.5 upon 0.1565, which is equal to 3.19. We use the relevant Z value to calculate the above probability. Similarly, when the population distribution of the sample is not normal, but the sample size is sufficiently large, we use the Z tables to calculate the above kind of probabilities. In this module, we discuss relevance and applications of the t-test, the chi-square test and the f-test in determining the above discussed probabilities. These distributions are the distributions of variables derived from normal distribution random variables. Hence, these distributions are significantly related to normal distribution. After studying this module, you shall be able to 1. Know about T, chi-square and F distributions. 2. Understand the main applications of the above said distributions. 3. Identify the conditions under which the above distributions can be used. Let us begin by understanding chi-square distribution. One of the most important non-parametric tools is the chi-square test. It is an entire family of distributions. We take k independent random variables with standard normal distribution. Let this be z1, z2 up to zk. Then the statistic z equal to sigma zi square, I varying from 1 to k, is said to have chi-square distribution with k degrees of freedom. It has only one parameter called the degrees of freedom k. Degrees of freedom in general are denoted by nu, the Roman numeral. There is a different chi-square distribution for each degree of freedom. The chi-square probability distribution graph is depicted in the figure for different degrees of freedom. The figure represents the density function of chi-square variable with chi-square variable on the x-axis and density on the y-axis. The curve of probability function of chi-square distribution depends on degrees of freedom. As the degree of freedom change, the probability function also changes. The figure represents that as chi-square decreases, the probability function decreases very rapidly and tends to z equal to 0 in the limiting case as chi-square tends to infinity. In other words, the number of degrees of freedom increases, the distribution becomes increasingly symmetrical. Thus, chi-square axis is asymptotic to the probability curve. Let us now understand the characteristics of chi-square distribution. It has the following characteristics. First, the distribution is skewed and the skewness decreases as the degrees of freedom increase. That is, the skewness is inversely related to degrees of freedom. For few degrees of freedom, the distribution plot is highly skewed, and for large degrees of freedom, the distribution plot is less skewed and becomes more symmetrical. Secondly, for degrees of freedom greater than 30, the distribution plot can be approximated by a normal distribution curve by standardizing the z statistic using the mean and variance of chi-square distribution nu and 2nu respectively. Hence, z is equal to chi-square minus k upon root 2k is calculated to determine area under the standard curve to find the probability of the z value. And thirdly, the sum of two chi-square variables with n1 and n2 degrees of freedom is also a chi-square random variable with n1 plus n2 degrees of freedom. Moving on to the sampling distribution of sample variance. Chi-square distribution is used to explain the sampling distribution of sample variance. Taking a random sample y1, y2 up to yn from a normal distribution population with mean mu and variance sigma square provides the following sample variance. S square is equal to sigma y minus y prime whole square upon n minus 1. If x prime and s square are the mean and variance of a random sample of size n from a normal distribution with mean mu and standard deviation rho, then 1. X prime and s square are independent. 2. The random variable n minus 1 into s square upon rho has chi-square distribution with n minus 1 degrees of freedom. Using the above results, we can determine the probability of obtaining greater than or equal to the sample variance. Using the statistical tables, we can determine the range within which this probability lies because of limited alpha, the level of significance values. Further, we shall now discuss t distribution. The t distribution is a probability distribution that is used to estimate population parameters when the sample size is small and or when the population variance is unknown. The distribution of following t equal to z slash under root y slash nu, where y and z are independent random variables and y has chi-square distribution with nu degrees of freedom and z has standard normal distribution. 2 is called t distribution with v degrees of freedom. The t distribution has been depicted in the figure. The figure shows the t distribution for selected degrees of freedom. It shows that t distribution, like the normal distribution, is symmetrical, but is flatter than the normal distribution. For degrees of freedom k equal to 120, the curve follows a normal distribution and hence it is a z curve. For degrees of freedom k equal to 20 and k equal to 5, the t curves are also shown. It can be seen that as degrees of freedom increases, the spread of the corresponding t curve decreases, that is, the spread of the t curve with k is equal to 20 is less than the spread of t curve with k equal to 5. Hence, as the degrees of freedom increases, the t distribution approximates the normal distribution. Any particular t distribution results from specifying the value of a single parameter called the number of degrees of freedom. We denote this by nu. Possible values of nu are the positive integers 1, 2, 3 and so on. So there is a t distribution with 1 degree of freedom, another with 2 degrees of freedom, yet another with 3 degrees of freedom and so on. For any fixed value of nu, the density function that specifies the associated t curve is even more complicated than the normal density function. Let us now look at the properties of t distribution. It has the following properties. First, the t curve is bell-shaped and centered at 0. Second, the mean and the variance of t distribution are 0 and nu upon nu minus 2 respectively. Third, the distribution is symmetrical like normal distribution, but its tails are flatter as compared to normal distribution, implying higher probability for extreme t values than the standard normal distribution. And last, as degrees of freedom reach infinity, the t distribution becomes identical to standard normal distribution. It has already been discussed that the random sample size of n taken from a normal distribution population with population mean equal to mu and variance equal to sigma square, the random variable x prime has a normal distribution with mean mu and variance sigma square upon n. Or we can say that z statistic x prime minus mu slash rho slash under root n has standard normal distribution. However, when the population variance is unknown, it is replaced with sample variance. The t distribution thus discusses the exact distribution of x prime minus mu slash s slash square root n for random samples taken from normal distribution population when population standard deviation is unknown. Let us now look at the rationale for t distribution. Based on the theorems learnt, we can conclude the following. If x prime and s square are the mean and variance of random sample of size n from a normal population with mean and variance sigma square, then t is equal to x prime minus mu slash s slash square root n has t distribution with n minus 1 degrees of freedom. Here z is equal to x prime minus mu slash sigma slash square root n and has the standard normal distribution. This is because S is based on the n deviations, which implies that only n minus 1 of these are freely determined. The number of degrees of freedom for a t variable is the number of freely determined deviations on which the estimated standard deviation in the denominator of t statistic is based. Y is equal to n minus 1 s square upon sigma square has chi-square distribution with n minus 1 degrees of freedom, and x prime and s square are independent. T distribution tables give the area to the right of the specified t value and degree of freedom. Hence, for 20 degrees of freedom, the probability of getting a t value greater than 2.086 is 0.025. Using the above results, we can determine the probability of obtaining greater than or equal to the given sample mean when only sample standard deviation is available. Using statistical tables, we can determine the range within which this probability lies because of limited alpha values. Now moving on to F distribution definition. There is an important connection between an F variable and chi-squared variables. If we take two independent chi-square variables z1 and z2 with k1 and k2 degrees of freedom respectively, the random variable f is equal to z1 upon k1 whole upon z2 slash k2, the ratio of the two chi-squared variables divided by the respective degrees of freedom can be shown to have an F distribution. F is equal to z1 upon k1 slash z2 upon k2 is said to be following F distribution with k1 and k2 degrees of freedom. K1 is the numerator of degrees of freedom, k2 is the denominator degrees of freedom. K1 and k2 are positive integers. A random variable that has an F distribution cannot assume a negative value. The F distribution has been depicted in the figure. In the diagram, the F distribution for various degrees of freedom has been shown. The curve F 50-50 represents the F distribution with 50 numerator degrees of freedom and 50 denominator degrees of freedom. Similarly, F10, 2 represents F distribution with 10 numerator degrees of freedom and 2 denominator degrees of freedom. Moving to the properties of F distribution. It has the following properties. First, the mean and variance of F distribution are k2 upon k2 minus 2 and 2k2 square multiplied by k1 plus k2 minus 2 whole upon k1 into k2 minus 2 whole square into k2 minus 4 respectively. This is defined for k2 greater than 4 for denominator to be non-zero. Second, the distribution of probabilities of f along f values is skewed to the right and approaches normal distribution as both the degrees of freedom become large. Third, it can be shown that a square of t distributed random variables with k degrees of freedom has f distribution with 1 and k degrees of freedom. And lastly, it can also be shown that f of nu1, infinity is equal to chi-square nu1 upon nu1, which implies that for large denominator values of degrees of freedom of S distribution, the chi-square value with numerator degrees of freedom divided by the numerator degrees of freedom are approximately equal. Further, we shall discuss the uses of F distribution. If S1 square and S2 square are the variances of independent random samples of size n1 and n2 from normal populations with variance sigma 1 square and sigma 2 square, then F is equal to S1 square upon sigma 1 square slash S2 square upon sigma 2 square, which is equal to sigma 2 square S1 square upon sigma 1 square S2 square, is a random variable having an F distribution with n1 minus 1 and n2 minus 1 degrees of freedom. F distribution tables give areas under the F curve to the right of the specified F value and degrees of freedom. For example, F value for 0.05 level of significance and K1 equal to 6 and K2 equal to 10 is 3.22. This implies that at the F value calculated from the above method and 6 and 10 degrees of freedom, the probability of achieving a value of 3.22 and greater is 0.05 or 5%. The table provides F values for few levels of significance. In order to find values for the other levels of significance, we use the following results. F of 1 minus alpha nu1 nu2 is equal to 1 upon F alpha nu2 nu1. Thus, in order to obtain the value of F of 0.95, 6, 10, the F value that captures 95% of the area of the curve to its right and hence 5% to its left, we can find the value of F for 0.05 level of significance and 10 and 6 degrees of freedom. This gives the value of 4.06. Hence, F of 0.95, 6, 10 is equal to 1 upon 4.06, which is equal to 0.246. Using the above results, we can determine the probability of obtaining greater than or equal to or less than and equal to the given sample variance ratio. Using statistical tables, we can determine the range within which this probability lies because of limited alpha values. Let us now summarize what we have learned in this module. The t distribution is a probability distribution that is used to estimate population parameters when the sample size is small and or when the population variance is unknown. T is equal to x prime minus mu slash s slash square root n when x dash is the sample mean, mu is the population mean and s is sample standard deviation and n is the sample size, has t distribution. The tables of t distribution are hence used in the case when the population standard deviation is not known and only sample standard deviation is known to compute the confidence intervals for mean. The random variable n minus 1 s square slash sigma has chi-square distribution when n minus 1 degrees of freedom. Hence, chi-square distribution tables are used to compute the confidence intervals for population standard deviation. Chi-square distribution is skewed and the skewness decreases as the degrees of freedom increase. F is equal to S1 square upon sigma 1 square whole upon S2 square slash sigma 2 square. This is further equal to sigma 2 square S1 square upon sigma 1 square S2 square is a random variable having F distribution with n1 minus 1 and n2 minus 1 degrees of freedom. Hence, F tables are used to compute the confidence intervals for sigma 1 square upon sigma 2 square.